My name is Maria Ignacia Lucares, architect with a master's degree in architectural design. This interdisciplinary research uses a process of mechanical extrusion and pressing to incorporate titanium dioxide nanoparticles into a recycled PET plastic film in order to explore the potential for a new building envelope material with the capacity to degrade atmospheric contaminant gases. The construction industry has embraced the notion of incorporating photocatalysis nanoparticles into architectural materials based on their capacity to degrade contaminants such as carbon monoxide, nitrogen oxide, volatile organic compounds, formaldehyde, and other industrial emissions. According to data from the Iberian Association of Photocatalysts, the principal applications for photocatalytic materials were paved surface, facades, interior surface, and roofing. The most commonly used photocatalytic facade surfaces include ceramic coatings and panels. Our focus on the building envelope as the subject of exploratory research into plastic reuse is to expand this emerging field of applications with the design of a new photocatalytic PET material. Atmospheric contamination in urban areas remains one of the most severe environmental problems facing the fields of architecture and urban sustainability. On the global level, OECD estimates for 2050 suggest that poor air quality in cities may become the principal environmental cause of illness and death. In light of this, one of the objectives of architectural and material design should be to develop solutions to mitigate atmospheric contamination in urban centers. The present research seeks to explore the possibility of creating a material with response to photocatalytic capacity to degrade atmospheric contaminants. Reintroduction of materials into production cycles have identified waste as a potential secondary raw material. Within this new cyclical notion of raw materials, plastic waste has been identified and documented as a political and an environmental issue. But how does the new material behave in terms of fertility and calcination? Does the process result in presence of titanium dioxide nanoparticles at the surface of the new material? As can be seen, PET waste is prepared by means of a mechanical process of grinding and washing and readiness to be mixed with the catalyst nanoparticles in an extruder, where temperature, pressure, and rotation speed variables are iteratively adjusted to achieve an optimal mixture. The newly extruded material, known as master batch, is then pelletized. Finally, the pellets are pressed according to different configurations of temperature, contacting time, and cooling time. Component proportions and a number of variables relating to the mixing process itself were found to be crucial to ensuring the stability of the new material. We succeed in establishing the optimum temperature and mixing duration for thermofusion and extrusion of the components. A larger proportion of nanoparticles results in a more fragile master batch with reduced elasticity, while the incorporation of too few nanoparticles will diminish the photocatalytic properties of the material surface. Having mechanically combined the two components, the resulting master batch is then pressed according to certain temperature, pressure, cooling time, and pressing time variables to produce films with dimensions in accordance with the Chilean testing standards. Change to the pressing variable results in different behaviors. The amount of moisture absorbed by the master batch must be less than 4%, as greater humidity results in increased fertility. The distribution of pelletized master batch on the pressing plates is another variable that affects the behavior of the film. The pressed film reveals the presence of surface bubbles as a result of uneven distribution of pellets on the pressing plates. Difference in film coloration are observed according to thermal treatment of the material during pressing. Temperatures higher than 260 Celsius degree result in calcination at the edge of the film and directly affect the mechanical properties of material. Following incorporation of titanium dioxide nanoparticles, the chemical behavior of the mixture was analyzed. Electron microscopy analysis of the samples revealed a distribution of nanoparticles throughout the film, thus validating the proposed combination of recycled PET with titanium dioxide to achieve a photocatalytic building envelope material. Greater surface roughness that will increase the area of contact between the film and the air. Incorporation of 8% titanium dioxide nanoparticles result in a loss of the original viscosity and elasticity of the recycled PET. These observations constitute a basis for the future studies into nanoparticles' weights and proportions in order to improve compatibility of the two elements. Using electronic microscopy, we were able to identify varying distributions of nanoparticles throughout the recycling PET film according to different configurations of production process, thus confirming the potential for the creation of a recycled polymer for photocatalytic applications. In the current state of this research, this film development is understood as a semi-finished product. Therefore, to validate a proof of concept, it's necessary the elaboration of exploratory films in accordance with Chilean testing standard NCH 873 to validate and move towards a building exterior prototype.